Okay, thank you very much, everyone, for coming in. This is basically this is the wrap up lecture on digital signal processing. There will be no math involved in this last lecture because we only have like 30 minutes. And in this lecture, we will only focus on. I want to make like a nice bow tie, yeah, to the whole course and give you some visualization to understand better the concept of Z transform, especially, and also a little bit about Fourier transform, maybe. So let's just start. I think to help me with this, I basically built this kind of simulation, yeah, some visualization um, to let us know about to let us go deeper into the understanding of the Fourier transform and Z transform. But for now, we'll focus on module 1 and module 5. But just to refresh a little bit, yeah, Fourier transform that we learned in the SP classes before, yeah, actually tells you the frequency components of a signal. So, hang on, let me share my screen. I think I forgot to share my screen. So, yeah. So basically, yeah, yeah. So here, as you can see on the screen, if I have a pure sinusoid signal with the frequency of 10 hertz, the FFT spectrum will be will have a peak, yeah, single peak at 10 hertz. Yeah. And if I change this frequency, as you can see, this FFT spectrum actually move. Yeah. The peaks actually move. And if I have like two frequencies like this, two signals with two frequencies, 10 and 25 hertz, the Fourier transform spectrum actually also shows you the two components at 10 and 25. And likewise, if I have more than two, like for example, three frequencies like this combined into one, yeah, and then in time domain, the signals will be combined into like this upper right signal. And then in the FFT spectrum, you can see that we have three peaks, yeah, at 5, 10, and 15. Okay, and again, if we change the frequency of one of the component, that component actually move in the FFT spectrum to the actual frequency. While the amplitude actually shows you the contribution of each one of these frequency component. So it is a nice visualization for that. Yeah. So the Fourier transform gives you the components, the frequency components of a time domain signal. So you can actually extract different frequency components this way. Now, one limitation of FFT transform, like we discussed in class, is that it only is applicable for a system if we want to use this Fourier transform DTFT, the discrete time Fourier transform on a DT signal, sorry, a DT system. It can only work for a system that is stable. If a system is unstable, or even marginally stable, oh sorry, just unstable. Yeah. If the system is unstable, the DTFT does not exist, so we cannot perform this kind of analysis. Which is why, just like how Laplace transform generalize the continuous time Fourier transform, Z transform generalize the discrete time Fourier transform. Okay, so let's go to the module 5, which is the Z transform. So again, here, the Z transform is nothing new. Yeah, it's basically just the generalization of the Fourier transform. It looks like this, yeah. So instead of just using like one-dimensional graph, we actually perform the analysis on a two-dimensional complex plane. Typically, we call this Z plane. And in class sessions, we already discussed the mathematical model of the Z transform. It looks like this, more or less, yeah. This is called the rational form of it, yeah. And from this, you see we have zeros that denoted by this zi and poles denoted by this pi. Okay, and as I mentioned in class, also we have this concept called ROC, which defines the regions of z, yeah, the values of z that will ensure that our um, z transform actually converge. So it approach something, a value, right? So for example, In this kind of, if you're given this pole zero configuration, we have this zero here, and then we have a single pole here. Yeah, there are two possible ROC, right? Either the ROC is actually going inward, like this one, z less than 0.922, yeah, because that tells you that all the values inside this green region will make the h of z finite, right? Or another possibilities is that we can have something like this, right? So now the ROC is z greater than 0.922. So now that means all the values of z in this green region actually make sure that our h of z converge. So that's what we learn in class, yeah. And also in class, I actually try to hammer it down, yeah. Like let me add a single pole here. Let me add a single pole here. That the ROC is the region on which the z transform actually provides a finite value. Yeah, that means this denominator is not zero. Yeah, the values of p that will make this denominator to be non-zero, yeah, is supposed to be the part of the ROC. That would mean, conversely, if p is in such a way that will make this denominator to be zero, we've got this hz to be infinite, or it blows up, basically, right? So that would also tell you that in defining the ROC, we cannot have the ROC to be including this pole. So, for example, like this one, it's not possible, right? So this pole is the forbidden pole. We cannot have a pole inside the ROC. But this is valid because now neither of the poles are inside this green region. We don't care about zeros, yeah. We don't care about zeros. I can move the zeros anywhere. It doesn't change the validity of the ROC, right? Now, if there's actually another possibilities, right, for this kind of ROC or for this kind of configuration, here's another possibility, right? So in this case, now the ROC is actually going inward, yeah, towards the origin. Or another possibility is that something like this, right? Now the ROC is actually growing outward from the outermost pole towards infinity. And the cool thing about this kind of Z transform analysis is that it tells you what kind of system that you have if you are talking about the Z transform of an impulse response, right? The HZ. So, for example, if you have something like this, yeah, that the ROC actually spreading outward, including the infinity, that means your system is actually causal and right-sided. And more importantly, here you can see there is this unit circle, yeah, a circle of radius 1, yeah, using this black dashed line. Okay, and this unit circle is very important because this is the Fourier transform circle, I would say. Basically, this is where the Fourier transform is defined. So, if you want to define the Fourier transform, the DTFT, yeah, the discrete time Fourier transform, you can simply take the Z transform and evaluate it for the values of Z that lies along this unit circle. Okay, so Fourier transform, the discrete time Fourier transform is just Z transform evaluated along that unit circle, which also means that if you have a system and you know it's Z transform, in order for the Fourier transform, yeah, of the system to be well defined, the ROC of your Z transform must include the unit circle. So in this case, as you can see, if the ROC actually includes this unit circle, we have this magnitude response. Yeah, this is basically the magnitude of your Fourier transform. Why? Because the unit circle is actually inside our ROC. So if I move this pole inward like this, that's also okay, right? We still have the magnetic response. However, if I move this pole, hang on, let me try to drag this pole outward like this now, the frequency response is unavailable because now the unit circle is not part of our ROC. So we cannot define the Fourier transform. Yeah. And in other words, it is also unstable. So stability can also be seen from the Z transform from the fact whether the unit circle is included in the ROC or not. Okay. That's about the ROC. Yeah. And from this Z transform, we can also define the sidedness, like I said, yeah. So for example, hang on, let me drag this circle. So for example, if I have, oops, sorry, if I have the ROC to be like this, that means the ROC is actually going inward towards the origin, then this system is said to be left-sided. Okay, and if the ROC is actually going outward like this, then we say that the system is actually right-sided. Yeah, so it's actually growing outward like that from the circle. However, we can also have a two-sided signal. Yeah, so for example, I can drag this one over here. So this is two-sided signal. Is it stable? Yes, because this includes a unit circle. Yeah, the ROC includes unit circle, but it is not causal. Yeah, the system is not causal. Here on the left, you can see it's actually no causal, not causal. Why? Because it does not include infinity. Okay, so the Z transform is very useful in designing your digital device. Yeah, like if you want to build a digital filter, you can actually utilize this. Yeah. So for example, you want to make like this, yeah, a two-sided system, and then you can just arrange the zeros somewhere to actually control the magnitude of your response, yeah, such that when omega is close to zero, sorry, or such that when the value is close to the zeros, yeah, you can actually find the magnitude that you actually want, right? Because the zeros is actually happening when this zi is such a way that z minus zi here will be basically the numerator will be zero, right? And here we have some other example, yeah. So for example, we can have something like this complex conjugate pair, right? What is the possible ROC? Well, it cannot be this one, right? It cannot be this one because the ROC actually includes two poles, which should not happen. So another possibility is that maybe like this. This is possible ROC, right? So it is possible ROC. However, this system is unstable. Why? Because it simply does not include the unit circle. Okay. If I want to make this system to be stable, then I need to drag this pole outside, maybe around here, and maybe this one also around here, right? Now this is possible. This is stable ROC. Okay. Now, is it possible for this system to be both stable and causal? What do you think?
I think it's possible, sir. Maybe, yeah.
Possible?
But
Well,
I
if
think
it's
so.
if it's stable, that means the unit circle must be included. Yeah, Matthew. Yeah.
Uh,
If if
yeah.
if this is stable, the ROC should include the unit circle. If it's causal, that means the ROC should also include the infinity. So it's actually going upward. So let's try to drag it
Oh,
in any way we can. Well, I can only put my my inner circle around here, right? So this is not possible here. This is the forbidden pole. inside the ROC, so I need to drag it a little bit further this way. So this is causal, right? This is causal. But is it stable? No, it is not, right?
No.
So
No.
how do we make it stable? Well, I have to put this, because there is no pole inside this unit circle, I have to put the inner circle to be at the origin. But that way, we actually have forbidden poles inside our ROC. So we have to
Uh-huh.
drag this outer circle inward like this. And it's still forbidden. So let me just bring this inward again. Now it's working properly. But now the system is no longer causal because it does not include infinity. Yeah, so
Okay.
that's what we mean. Yeah. So in this case, if you know the configuration of the pole and zeros, yeah, especially the poles, well, you know what kind of system that you can have. Can you have both stable and causal? Yeah, like that. So it determines what kind of
So what if
system.
we
Yeah.
put the post inside the unit circle? Will it still
Well,
be stable and causal?
like this, right? If you we
Uh-huh.
still have three, if you still have three poles like this, well, you can just play around. Yeah. How do we make this? How do we enforce this to be stable? Well, I have to drag it like this. Well, that's not possible because that means we have forbidden zero here, forbidden pole here, right? But I can
Mm.
pull it like this. It is stable now, right? It is stable. However, it's not causal. How do we make it causal? We have to include infinity. So here we have two forbidden poles. So I need to drag this inner circle outward like this. That will make it causal. But see, now we left the unit circle. So it's no longer stable. So for this kind of configuration, for this kind of pole zero plot, it is impossible for us to have both stable and causal. So we need to arrange the pole in some other way. For example,
Okay.
like you suggested before, yeah, maybe I want to have this to be ROC, so I need to delete this pole. I need to delete this pole and then delete this pole. Now it becomes both stable and causal. Clear?
Please, sir.
Okay, like that. Okay, so I think that's basically it. Yeah, that I want to wrap up. Yeah, using this visualization to really let you imagine how the pole and zeros play in determining the behavior of the system. Yeah, because in Earth engine that's very important. Yeah, because the position of the pole and zero, and also the whether we have zero or pole. Yeah, at all. Yeah, how many zeros we have, how many pole we have. It actually determines what kind of component that we have in the system. Okay, I think you learn in LCA, yeah, electrical analysis, that if we have a capacitor, we can convert the impedance of this capacitor to Laplace transform, yeah, using Laplace transform in Laplace domain. Inductor can also be done like that, and this will introduce pole and zero. So this is basically the same way. Yeah. In the only difference is that instead of working in time domain, like the circuit analysis, now we are working in frequency domain. Sorry, the discrete time domain. Yeah, my bad. So instead of continuous domain, it's in the continuous time domain, it's in the discrete time domain. But the way that we do this is still the same. So if we discretize, yeah, our system, yeah, and then we can determine what are the poles and zeros, yeah, then we can determine what kind of behavior the system impose, yeah. And if we want to change this behavior, we just need to change the pole and zeros and try to think about what kind of components that we need to change from our circuit. Yeah, that's basically the design problem, which is assisted by these transformations. Okay. Likewise, if you want to build a filter, if you want to build a digital filter, low pass filter, high pass filter, band pass filter, yeah, for example, for digital signal processing, then you can start by thinking about the configuration of pole and zeros, and then from there you can actually determine what kind of um, equation, yeah, your system has, and then from that, how do you implement it programmatically, yeah, or maybe using some logic gates, yeah, and so on. So yeah, I think that's all that I want to say. Yeah, is there any question from you? Maybe we have one question, and after that,
Can I ask
yeah,
you?
yeah, I do.
I think you mentioned it at the beginning also. We can only get DTFT for a stable system.
Yeah.
But isn't there an exception if I recall?
Sorry, what? Is that what?
Isn't isn't that we can only get a DTFT of a system if it is stable, right?
Yes. Mhm.
But if I recall correctly, in our class, isn't there an exception to this rule?
Yeah, there is actually an exception, but the exception is not related to um. Yeah, the exception is just about some signals. Yeah, like the unit step. Yeah, unit step signal is actually unstable, but we can define the DTFT for computation for the signal. But yeah, you are right. Yeah, there are some exceptions, but it's very tiny. Yeah? Just some signals that we can actually massage a little bit. Yeah, so that we can actually define the DTFT. Okay.
Okay.
Yeah. It will be interesting. Yeah, you can well. This is not going to be homework because we don't have time to actually submit the homework. But you can think about if I have UN, yeah, unit step. How would the pole zero look like for that Hn equals to Un? What is the Z transform of that? And then you can draw the pole zero. And then from that, you can actually determine possible ROC. And then from that, you can determine whether it's actually stable or not from the point of view of the Z plane. It's going to be interesting exercise. Okay. But for now, I would like us to close this session with a small quiz. I hope you can see my screen, yeah? And please pull up your phone and join in. I will give you 2 minutes. Okay, maybe let's just start. Yeah. Okay, let's start. Oops. Oh, sorry. I think the Zoom is about to end. Yeah. Okay, good. Show answers. Okay, good. Everyone answered correctly. Okay. I'm sorry, but I think the Zoom is actually ending because oh no, we still have like 9 minutes. Yeah. I think yeah. So maybe we can just continue. Let's continue. Oh yeah, because we have until 11:40. Yeah. 2, 1. Okay, the answer is oh, a lot of you actually answered correctly. Hang on, let me check this one. Yeah. So this this ROC, as you can see, yeah, it actually spreads out from the outermost pole towards infinity, right? So the system is causal. Yeah. If it is not causal, then it will not actually spread out to infinity. It either goes down, yeah, goes inward towards the uh, unit circle, towards the origin, or it forms a ring. In this case, the ring will include the unit circle. Okay. So in terms of causality, since our arrow is actually spreading out from the outermost pole, including the towards the infinity, that means our system is actually causal in this case. Okay. Be careful. Okay. The system is causal. Yeah, not non-causal. Okay, let's continue. Yes or no? What is done with the SRC is stable. Sorry, does it have? Okay, good. Most of you answered correctly. Yeah. So it does have the TFT. Yeah, because the ROC actually includes the unit circle. Very good. Next one, I think this is the last one. Yeah, this is the last one. Which among these four ROCs describe a two-sided stable system? Okay, 10 seconds to go. Okay. Oh, still some of you answered A. Yeah. Okay, still wrong. Okay. So two-sided means that our ROC is in the form of a ring. Okay, so that already eliminates number two and number option B and option D because they are not a ring. Yeah, this ROC actually is just going out towards infinity. This one is actually going inward to the origin, so these two are not a ring. Yeah, the ROC does not form a ring. So B and D cannot be two-sided. So what about A and C? Well, these two, well, number A is also not ring, yeah. So that leave only number C actually. The only two, yeah, the only ROC that actually forms a ring is actually number C. And as you can see, the unit circle is already inside this ROC. So it is stable. Okay, so the answer is actually C. Yeah, so be careful, yeah. If you see the requirement for system to be stable, you should already know that, okay, we are talking about the ROC that includes unit circle. If we are talking about two-sided system or two-sided signal, you should already have in your head that, okay, the ROC should forms a ring. Okay, just as simple as that. Okay. So anyway, this is the end of this quiz, and let's see who got the first place. Hey, Matthew. Congrats. And also Alan, yeah. Good. And Gania for the third one. Third place. Very good. So yeah, I think that's actually it for today. Yeah. Um, Again, like I said, this is just a wrap up course, something to um, wrap your head around, yeah, and maybe just connect the dots, yeah. Maybe in class we all talk about mathematics, yeah, and then I draw some stuff, yeah, but hopefully with this kind of cleaner visualization, now you get an idea about what is Z transform, how does it relate to the discrete time Fourier transform, and how it is possible to actually use it in practice, yeah. Well, we did not actually get to that last point yet, but I think you can imagine it for now, yeah. And maybe next time when we have time, we can continue, yeah, with this kind of topic, yeah. So yeah, I think that's all for today. Yeah, thank you very much, everyone. Yeah, I appreciate you coming here today, and I think that's all for today. Thank you very much, everyone. Yeah, thank you, and I'll see you next time.